We are talking about introduction to reliability in the advanced marine structures program in module 3. In the last lecture we said that the reliability analysis cannot be 100% accurate because of mainly 3 reasons. The first reason what we understood was all uncertainties cannot be accounted for. It is not practical to account for all uncertainties in the analysis and design associated with the material characteristics as well as the load effects. The second reason why the reliability methods cannot be 100% accurate is the analysis and design tools I can also say the modeling aspects, because analysis requires modeling, have lot of uncertainties. Generally they are handled by idealizations or structural assumptions. To address them, and these assumptions impose limitation to reliability methods, not making them 100% accurate. The third reason why we said it cannot be 100% accurate is the integration of the probability density function within the failure domain is complex. So, because of these 3 associated reasons, one can say that the reliability methods cannot be 100% accurate. Therefore, there are some basic degrees of simplification made in the reliability analysis. So, one must agree that the reliability analysis or reliability methods of analysis and design is not 100% accurate. There are some degrees of simplifications made in this. Now, let us ask the next question, which is question number 1 in this lecture, is that why reliability is important for marine structures. Why is it important for marine structures? There are many reasons. We will talk only about the critical reasons why they are important. 1, marine structures are subjected to a variety of environmental loads the load effects are highly uncertain. We have understood from the first module that these loads cannot be predicted or assessed accurately. Only they can be assessed probabilistically. That is what we call as characteristic loads. Characteristic load by definition gives me a meaning that the load associated or assessed by this technique is said that they will not exceed beyond 5% of exceedance of the values what you have used for the design calculations. With 95% they will agree with the values what you have assessed. There is always a probability of only 5% of these loads getting exceeded in the service time. The second reason why reliability studies are important for marine structures, one aspect is about the load effects. The other aspect is material characteristics in terms of the yield value, the Young's modulus, I should say Young's modulus static, and I will also say Young's modulus dynamic. We will talk about this in this lecture today. You may wonder, sir, we are using steel as one of the most advantageous and let us say friendly material for marine structures. For steel generally yield values or Young's modulus are well defined. Why we are using this as one of the importance for using reliability, because reliability is a term associated with probability, then why are we using this? We already understand that we also use what we call characteristic strength of material, what does it mean is the material strength will not vary beyond 5% in a given sample. 95% the strength will agree or the materials will agree to the estimated value of these. So, there is a 5% probability variation, therefore, we say that the material characteristics will also vary. Thirdly, material degradation, that is loss of material strength with respect to age is not assessed with 100% accuracy. There is a problem. Thirdly, the load combination effects. Results in high probability of variations in the failure modes. We have already seen this. Failure modes under axial tension, axial compression, failure modes in shear, failure modes in torsion, failure modes in buckling combined with axial load, they are all different. Okay? There is a high level of variation. So, these variations lead to uncertainties, even in the failure modes of marine structures. More interestingly and most importantly, marine structures are heading towards new, I should say innovative geometric forms, or I should say structural form. In such forms, the basic problem is stability preluding, or let us say stability preceding with the bending or axial tension or compression failure. Formation of local stresses due to stress concentration factors activated because of different material compositions. What I mean to say is composite material, because composites are used now in a very larger order for new form of marine structures. So, now there should be a mechanism to account for all these uncertainties, all these probabilistic values in terms of load effect, in terms of material strength, in terms of new form, geometric form of structure, as well as account for different modes or methods of failure. Okay. So, reliability is the only tool which can address these uncertainties using probabilistic tools. Hence, reliability study is very important and very critical for marine structures. Now, more interestingly, we can also make another statement: even if the analysis is highly rational, you may think it is highly accurate. The analysis what you are using is highly accurate or very highly mathematical and rational. Even if it is highly rational, it is better to use reliability analysis, because every analysis tool will have assumptions, and these assumptions will always lead to uncertainties, and these uncertainties can very well mathematically and effectively handled in reliability methods. Therefore, it is very important that I must use reliability technique for analyzing marine structures. Any questions here? Question number 2, when we talk about reliability, we always talk about the converse of failure. Let us now compare or contrast failure and reliability. Let us compare and contrast failure and reliability. Now, if you look at the definition of failure, it is generally expressed in probabilistic terms. Now, you may ask me a question, why it should be expressed in probabilistic terms? What is the necessity? Why? In a given design which is being done as an outcome of an effective, intelligent, efficient analysis, you cannot say the structure is going to fail for sure. The moment you say failure is 100% going to happen to the structure, either the design is wrong or the analysis methodology is wrong. You can always make a guess what is the probability that the structure may fail. So, failure is always expressed only in probabilistic terms. Okay. Now, it is assessed, failure is assessed, okay, as inability of the structure to perform its intended function with adequate capacity for a specified period of time under specified conditions. It is very interesting to understand the key words of this definition first. I am talking about failure. We have already said failure cannot be expressed in definite terms, because if the failure can be expressed in definite terms, either your design is wrong or the analysis methodology based on which you have designed the structure is wrong. So, structure cannot be considered as 100% to fail, okay, under any given instance. So, you can always express only this in a probabilistic term, right. So, failure is a method of assessment, it is not analyzing, okay, it is assessing, okay, you are estimating. Now, the structure is designed to perform certain function, the structure is designed to perform certain function, the structure is failed, that is why it is called failure. The structure is failed to perform that function adequately, it is performing, but not to a satisfactory limit, okay, adequately. And when do you say the structure has failed to perform its function adequately? Only within a specified period under specified conditions. So, you must specify the condition at which or under which the structure should perform. You should also specify the period up to which the structure should perform satisfactorily, and under the definition of period and condition, if the structure has shown its inability to perform, then we can say the structure has failed probably. So, most importantly, failure cannot be assessed on a structural system for an infinite period of time under any guessed condition. So, the period of time is generally what we call as lifetime of the structure or service period of the structure or annual period. Whatever may be the period of your design, we can call that as a specific period of time. So, it is very clear in the definition itself that failure cannot be assessed on a system on an infinite period of time, okay. You have to specify the period of time. On the other hand, when the period of time is exceeded, if the structure has shown its inability to perform its function adequately after the time is exceeded, it is not called as failure, okay. Alternatively, it is happening within the period of time, but the specified condition of loads, boundary condition, the C state has exceeded your predicted values, even then it is not considered as failure. Now, you have a structure, you have designed a structure based on critical analysis methodologies. The structure is within the service lifetime, maybe you have designed it for 25 years, it is 20th year running of the structure. The structure is showing or indicating its inability to perform the function. Okay. Now, the conditions have altered because you have not designed it for a specific wave period or wave height or a specific C state. Now, the C state is attacking or encountering the structure in a specific site. So, the structure has to fail, right, it will show its inability, but you cannot call that as a failure because it is happening within the period and you think it is happening within the specific condition. You think, you may not know actually, the specific condition is varied. Okay. So, then how will you address this failure, because you cannot call this as a failure at all by definition. Okay. Therefore, such situations are handled rationally in the discussion by using a term reliability. Okay. Reliability is a rescue term for failure. So, now interestingly, instead of saying you have failed in a class of 100, instead of saying 10 persons have failed, there is a positive way of making this statement. The teacher can always say 90% of people have passed. Okay. So, elimination is always taken on the positive dimension. Instead of saying you have failed, people can say you have not passed, meaning is same. So, now definition of failure is given on the contrary. Instead of saying failure, I will say reliability. The moment I say reliable, it means it is having some belief, some confidence. Okay. Then the definition should be slightly modified. Okay. So, definition of reliability is that it should be expressed again in probabilistic terms, because I am connecting failure to reliability. When failure is in probabilistic term, I should always say this in probabilistic terms. Okay. So, probability is associated to reliability because of two reasons. First and foremost reason is there are varieties of uncertainties which we saw in the last discussion, which cannot be handled otherwise rationally except tools of probability. So, probability is one of the important efficient tool through which reliability studies are conducted or carried out. The second reason is failure cannot be given in definite terms, failure can be only stated in probabilistic terms. Why? If you say the structure is going to definitely fail, then people will say either the design is wrong or analysis methodology is wrong or construction techniques are wrong. Okay. So, it is an error, it is not a failure. Failure is only when the inability of the structure is demonstrated explicitly, it is not able to demonstrate the adequate load carrying capacity within a specific period of time under specific conditions. So, now I am looking this aspect in a positive dimension, because failure is a negative dimension. So, that is what reliability is, it will be expressed in probabilistic terms. Therefore, it is the ability of the structure to perform the intended function with adequate capacity for a specific period of time under, this is R, under specified conditions. I am not altering any of the statement except saying, I am saying it is the ability, it is the capacity. So, therefore, reliability is generally 1 minus probability of failure. That is a general notion what people have in mind. Okay. Now, interestingly, I have a very critical question. Let me see who can answer this. What is the difference between safety and failure? First question is, what is the difference between safety and failure, or do you think are they same, safety and failure, or unsafe and failure, to be very clear, because they are different, means in what sense, how are they different, why two terms should exist in literature, safety and failure.
It is related to human
Not necessarily, you are telling only one dimension of this. Okay, this is a very interesting question, one must understand.
Getting the experience from the failure, we make the assumptions also.
Exactly, very good. Failure is an assessment based on judgment. Safety is an assessment based on mathematical concept or statistical concept. Okay? There is no judgment applied in safety. Judgment is applied only when it is a failure. So, there are two different terms. So, failure is a converse of reliability, or reliability is a converse of failure. Therefore, reliability is a process where judgment need to be applied. So, it is a science. Okay? It is not a method, it is a science. Reliability requires judgment because failure requires judgment. Okay? First answered. Second critical question, when failure is understood very well universally by engineers, then why a new term reliability explaining converse of failure should be introduced? What is the necessity? When failure is understood by the people, engineering community has understood what failure is. Okay? When people have agreed on this statement, then why one should introduce a new terminology, the reliability expressing converse of failure in the literature? What was the necessity? Very good. See, instead of saying a negation aspect on anything, reliability gives you a positive feedback of things. Is it clear? As I gave an example, in a class of 100, teacher may say 10 has failed, teacher may also say 90 have passed. So, saying 10 has failed is concept of failure, saying 90 has passed is reliability. So, reliability is a science of better presentation of failure, we can put it like this. Okay, it is a better presentation of failure. Okay. So, you will very well agree that whenever I speak about reliability analysis, I will always talk about failure only, but the answer is always given in terms of reliability, which is nothing but 1 minus probability of failure, that is all. So, there is no hairline difference in the techniques adopted for failure assessment and reliability assessment. Whenever I have to assess reliability studies or methods, I will always talk about failure only, but when I give the answer, I will give the answer in the converse form, just to have a better presentation of the answer. Okay. So, therefore, I can say reliability is expressed in terms of probability, because failure is always probable, cannot be definite. Now, what are the deliverables of a reliability study? If you conduct a reliability study, what you must get your answers? Okay. The foremost result what you must get from reliability study is a quality of performance is expected from the structure. What does it mean? When you say the structure is reliable by 90%, you are guaranteeing certain quality of functionality to the structure. Okay, is expected from the study. 2, it is expected, which is expected? The quality of performance is expected for a specified period of time. Usually this specific period of time is what we call as service life of the structure. Okay. What does it mean? It very clearly tells me that reliability study should not be carried out on structures whose lifetime is exceeded. Is it clear? It should not be carried out. Okay? The third deliverable of a reliability study will be, it is expected to perform under certain specified conditions. Therefore, reliability study cannot be used as a substitute for post accident scenario. What does it mean? When the platform has already failed because of accident, on the platform you cannot conduct reliability study. It is not an accident modeling at all. Why? Under accident modeling, the specified conditions of the design are exceeded or altered, that is why accident has occurred. Okay? On such situation, reliability should not be conducted. Okay? Now you will understand very clearly, under this condition and under this condition generally failure studies are conducted. Okay? When the platform has failed because of accident, you conduct a failure study. If you really want to assess the capacity of the structure after the service life is concerned, you talk about failure, but I say reliability is not recommended. Can you tell me why? Now it is a deviation from failure and reliability. Why? Why? Answer is within the definition of reliability itself. Please recollect this answer, I will give you the answer. The answer is very simple. Once the service life or the conditions are exceeded or altered, failure study can be invoked to diagnose the reasons why the failure has occurred. Agreed, because some study has to be carried out. Reliability cannot be carried out because, though it is a converse of probability of failure, mathematically it cannot be done because of a simple reason: the characteristic effects of load and material strength have altered seriously. So, reliability is only within a specific defined value of probability, that is, the load should not exceed beyond 5% of your calculated value and the strength should not deteriorate or degrade less than 5% of your characteristic value. If these conditions are altered, under that specified condition reliability should not be applied. Very clear? Is it very clear? Therefore, reliability is a failure study in the positive dimension under given specified conditions within a specific period of time, which usually people call a service life of the structure. Okay? Now, reliability studies cannot be extrapolated to extend the service life of the structure. Okay? Then the fundamental question comes, why at all reliability study should be carried out? What is the necessity? What is the necessity? It cannot be carried out when the service conditions are altered or the specific conditions are altered. It cannot be carried out to extrapolate the service life of the structure. Is it safe or unsafe? Safety and reliability are different things, we have already seen in the last lecture. Then why we conduct reliability? The question is again in the last lecture. The answer is very simple, I will give you the answer. Reliability is a part of risk assessment, because risk is nothing but probability of failure multiplied with the consequence, and reliability is 1 minus probability of failure. Okay? One is always interested to know what is the risk beyond the service life of the structure, what is the risk in the present state of service condition of the structure. Okay? The moment I say I will use failure study for this, risk is 100% because I am saying it is failed. I have to look this risk study in a positive presentation, which is reliability. Is it clear? So, reliability is having still its importance to claim or to declare the risk associated with the platforms, because risk is having a product of consequence of failure and probability of failure. Okay. Consequence of failure can be financial, societal, which we saw yesterday, but failure studies can be addressed in the converse manner using reliability. So, that one can say the risk is 80%, it means 20% more or less is reliable. Okay. Instead of saying 20% or 80% failed, 20% safe. Instead of saying using the term failure, we are using the term reliable. We are saying 20% reliable and so on so forth. So, it is having still a very deterministic meaning in terms of structural engineering applications on service life of the structure or accident modeling, etc. So, people conduct accident studies, which we call as quantitative risk assessment, accident modeling, etc., where reliability studies are all a part of this. Okay. Any questions here? Now, we spoke about reliability as an effective scheme of addressing different uncertainties. Okay. There are two types of uncertainties. First type, which arises from or those arise from randomness of the nature. In terms of load effects, because these are the natural phenomena which acts on the structure. For example, wave loads, wind loads, wind direction, wind speed, wave direction, wave velocity, wave height, wave period, okay, swelling effect, these are all natural phenomena and all of them are random in nature. Okay. There is a high randomness associated with the load effects. That is the first type of uncertainty. We call this as aleatory type. The specific problem or difficulty with this kind of uncertainty or this type of uncertainty is they need to be handled rationally in the design. There is no other way. You cannot get rid of this type of uncertainty. It is never possible to make this variation certain, it will be uncertain. So, you have got to handle this rationally. How? We use characteristic values associated with these loads and different combinations also, we have seen that also. Okay. When they are acting independently, when they are acting combinedly, then the effect of combination is also seen in the codes as different values, which we have seen in the unit 1 or module 1. So, they are handled rationally in the design. There is no other mechanism by which this randomness in nature can be addressed. Remember, even today there are no methods mathematically available to address this kind of uncertainty or this type of uncertainty in a more effective manner. Okay. The second aspect those arise from inaccuracies in prediction. They generally come from they originate from analysis methods, modeling constraints, etc. This type is called epistemic type. Spelling, please check this. This is epistemic type. They need to be reduced. Okay. One should control or reduce the effect of these kind of uncertainties or this type of uncertainty in the reliability analysis. One is beyond control, you handle them rationally. One is under control, handle them intelligently, okay, using effective mathematical tool. So, there are two types. I am not giving examples for these, I think you very well understand from the first module, from environmental loading 1, 2, 3, 4 and for material strength lectures in module 1, you have understood that how you can give examples of randomness in nature varying from the load effects and how we can say that the modeling aspects can be varying or originating from the modeling constraints and how they can create uncertainties. Now, let us talk about uncertainties, different kinds. There are types, okay, different kinds of uncertainties. The first kind is those arise from randomness and variations in exciting or excitation forces. Now, what is the difference between the randomness in nature, which is one of the type of uncertainty, and randomness in excitation force, which is uncertainty of the kind 1? What is the difference between these two? This uncertainty type talks about the process, this uncertainty type or kind talks about the mathematical representation of the process. Okay. This is originated in nature, okay. This is your difficulty, okay. Of course, they are irreducible. The second kind, statistical uncertainties, that arise from estimation of parameters describing the statistical models. Can you give me an example of this? Estimation of statistical parameters explaining the model. I am looking for a probability analysis. I would require the first order values at least, which is nothing but the mean and standard deviation. Mean and standard deviation are computed from an ensemble or a sample of the material or the load effects, etc. And there can be some statistical parameters like mean, standard deviation, variance, which you have computed, which are all parameters used in statistical models. There can be uncertainties associated in estimating this also. Okay. That is the second kind of uncertainty. Okay. They are reducible. Okay. There are effective tools available. You must use an appropriate model, can reduce the effect on this on the study. The third one is modeling uncertainties that arise from imperfections in mathematical modeling. There can be some error in a mathematical modeling techniques. They can also lead to certain uncertainties, and of course they should also be reducible. Now, the randomness and variations in the excitation force, which are essentially caused from nature, though you have taken an effective process to filter them, what I mean to say is you are looking for an 100-year return period of a design wave. The design wave is uncertain, there is a randomness associated with the design wave, but why 100 years, why not 50? You have seen in different quotes in the module 1. If you look at Canadian quote says use 50 years of return period, okay, and there are certain level of probability acceptance where the return period can go as high as 275 years also for earthquake, for example. We have seen this. Okay. There are literature which can explain you this. I have also written an equation in the first module explaining how the return period can be computed if you know the service life of the structure. So, these cannot be reduced, they are irreducible, fine. Now, at least these two which can be reduced, which is essentially what I call human errors, okay, errors created by mathematicians, statisticians, engineers, because the statistical parameters are not estimated correctly, the mathematical modeling is not done properly, it can create uncertainties. They should be reduced. Now, how are they handled? I am not explaining in detail, I will give only a tip, because this lecture is not talking about reliability alone, it is only a format of touching reliability as applied to marine structures in this course of advanced marine structures. Okay. Now, these kind of 213 can be handled effectively, I can even say efficiently, using Bayesian approach. You can use Bayesian approach to handle these, to address these. Now, immediately the question comes in mind is what is Bayesian approach? Okay, we will not discuss in detail, but anyway we will explain what Bayesian approach is. In Bayesian approach, models and model parameter. The moment I say model, they are mathematical models, not physical models. Okay? Models and model parameters are estimated using likelihood functions using these likelihood functions the posterior parameters of the models are calculated based on the model details of the previous one. It is expected that the error in this approach is minimum because the parameters are estimated from an established or existing models of large data. I can give a very simple example of this, very simple straightforward example. I want to analyze a deck plate. I can use different kinds of elements, model elements. I can use quadrilateral element, I can use a triangular element, I can use a shell element with 4 nodes, 8 nodes, 16 nodes, 24 nodes, etc. There are different types of models available, solid models and surface models, mathematical models available. All these are nothing but established existing models which has got a large amount of data which can now be used as likelihood functions, based on which you can derive these posterior parameters based on the previous ones. So, the error can get reduced. Okay. So, Bayesian approach is an algorithm which recommends you to use the likelihood functions as applied to the existing models and then derive the parameters as posterior information from the existing models. So, you keep on improving on the model. Instead of you start a new model, you pick up any one of the existing model, a set of existing models, and compare them, whether the B-spline curve is better, whether the parabolic curve is fitting better. Look at these models, keep on applying and minimize the error as maximum as possible, resulting from the mathematical formulation of the problem in terms of modeling. Okay? That is what Bayesian approach is. Most of the software which are used for modeling, finite element modeling, CFD analysis, etc., use mostly this kind of approach. Okay, it is a very interesting analysis given by Bayesian. It is an interesting algorithm. We are not discussing, as I said in the beginning, the algorithm in detail as applied to a problem, but that is how the error minimization happens in one of the or two kinds of uncertainties which are generally a high level of botheration in reliability analysis. Okay? Because one cannot do anything with the irreducible kind of uncertainty. Okay? Instead of worrying about that, whatever I can minimize, let me do that. Okay? That is what people have been doing in the engineering perspective in the reliability study in the recent past. Is it clear? We will extend this lecture in the next part, speaking what are those parameters which will influence reliability study more in detail in the next lecture. Okay? So, in this lecture we have understood that why reliability is important for marine structures, why reliability studies are not 100% accurate, what is difference between failure and reliability. If failure is understood well by an engineering community, why reliability term is at all introduced in engineering literature, how reliability cannot be applied to existing structures which has crossed the service period, then where is the question of risk applied to the structural system, why do you estimate risk on giving systems, then what are those kinds and types of uncertainties which bothers reliability study in detail. Okay? Thank you.